My name is Francesco De Zan. I'm working on INSAR at DLR. And in this session, we have 5 talks, and we have our 5 presenters already online. And at the end of this talks, we have 15 minutes Q&A section. You can already post your questions on the Slido chat, and you can also upvote them so that we can select the most popular in the discussion. When you post your question, you should add this @ and the name of the presenter. This simplifies the dispatching the questions. There's also a related poster session this afternoon on similar topics, so maybe you can also take a look at this. So I think we can start with the presenters. Okay, now we can see all of them. We can start briefly with the first presentation by Virginia Brancato. The title is UAV SAR Observation of INSAR Parametric Phase Diversity, Implications for NISAR Ionospheric Phase Estimation. So please, Virginia.
Does everyone hear me okay?
Yes, I can, yeah.
Okay, perfect. So welcome to the first presentation of this session. And so this talk will briefly summarize the work that me and my co-author Eresh Fattahi have been doing regarding the estimation of the ionospheric phase screen for NISAR L-band repeat pass data. NISAR is a dual frequency repeat pass SAR mission with fully polarimetric capability. The project will process and publicly distribute interferograms with a 12 days temporal baseline. So we all know that repeat pass L-band measurements are affected by changes in the microwave propagation through the ionosphere. This differential ionospheric delay, if not properly compensated, can introduce some spurious interferometric fringes. An example for an ALOS pulsar stack over Chile is reported like in the middle row of this of the figure on the right side. And if we do not compensate for ionosphere, this can degrade the accuracy of our deformation estimates. So NISAR decided to add a sideband of 5 megahertz to estimate the ionospheric phase screen using the split spectrum technique, where the range bandwidth of the SAR signal gets split into 2 subbands to form 2 low resolution interferograms at different center frequencies. Depending on the mode of operation of the NISAR radar, the sideband can be acquired either at the same polarization of the main band or at a different polarization than the sideband. For example, if the radar is transmitting in the so-called quasi-quad pole mode, where we transmitted 2 dual pole modes in the upper and lower part of the spectrum, then the main and the sideband will be acquired at a different polarization, for example, HH and VB. This means that for QQP repeat pass measurement, when we are going to estimate the ionospheric phase screen using the split spectrum technique, we not only will have interferograms at 2 different center frequencies, but also 2 different polarizations. So in this presentation, I want to discuss pretty much whether we can assume that interferogram at HH and VV polarization do not introduce any sort of inconsistencies into the ionosphere phase estimation. If this polarimetric diversity is present, what is the impact on the QQP repeat pass ionospheric phase estimation, and give recommendation for the NISAR mission? So we decided to focus our attention to characterize the special temporal pattern of the interpolarimetric diversity, so differences between interferogram and two different polarization on two data sets acquired by the JPL UABSAR L-band sensor. So we have two sets of fully polarimetric co-register stack of SLC acquired over agricultural areas in Canada. The difference between these two data sets, CANEX and SMAPVEX12, is the condition of the soil by the time of the UABSAR campaign. So for the CANEX campaign, the condition of the soil was bare. In other words, the vegetation cover was pretty much negligible. Conversely, for the SMAPVEX12 campaign, the vegetation changes dramatically throughout the UABSAR acquisitions. So our processing is very, very simple. So we have stack of co-register SLC. We form interferometric pairs between all the possible acquisition. And for each fixed interferometric pair, we do the difference between an HH and VV interferogram at the same center frequency. So we are focusing on the copolar channel, and we are assuming to regard like negligible the dispersing nature of the scattering process. So this slide shows an example of the HH minus VB INSAR phase inconsistencies for the CANEX campaign. So figure A, B, and C report the difference between an HH and a VB interferograms for an interferometric pair with 3 days, 7 days, and 12 days temporal baseline. We decided to filter out pixel whose coherent magnitude was lower than 0.5. So first thing to notice, we cannot assume that HH and VV interferograms are equal, but we do see inconsistency, polarimetric inconsistencies in the interferogram, which do not only vary temporally. As the temporal baseline increase, these inconsistencies become bigger, but they do also vary spatially. Particularly, they do exhibit a dependency on the incidence angle. So the shallower the incidence angle, the bigger in magnitude the discrepancies between the HH and VB interferograms. Overall, over 12 days temporal baseline, we do record HH minus VB phase inconsistencies between 15 and 30 degrees. Given the condition of the soil by the time of acquisition, we do suspect that these changes are driven by soil moisture effect and can be explained by the presence of a vertically stratified volume containing a soil moisture gradient. So this slide instead shows an example of the HH minus VB phase inconsistency for the SMAPVEX12 campaign. So at the center of the slide, I have HH minus VB phase difference for 12 days and 30 days in the rightmost part. So in this case, we also do see that the spatial temporal pattern of this change is very pronounced, not only in time, but also spatially. But we also see that pretty much these changes, they do cluster on a field basis. Particularly, if we look at the inset, like here, we do see that these changes do exhibit a different magnitude depending on the type of crop planted in a specific field. The other way to see this is to look at the scatter plot, which shows the HH minus VB phase difference as a function of the temporal baseline for different crop types. And pretty much each marker is color-coded by the phase standard deviation. In other words, we do see that for wheat, barley, canola, and to a certain extent cornfield, this HH minus VB phase difference, it appears to be pretty much pronounced. Well, instead for soybean fields, it's pretty much like very low. In other words, we do record record like differences between HH and BB interferogram over 12 days between 30 to 60 degrees. Given that these differences, they pop up over field characterized by vertically oriented vegetation, we do suspect that one reason that like gives up to these inconsistencies is birefringent propagation through the vegetation canopy. So we do see polarimetric discrepancies in SAR interferogram, and we do want to understand what is their impact on the QQP ionospheric phase estimation. So to do so, we consider an area over the Sant'Andreas Valley of 250 by 250 kilometers, roughly like the size of a nicer SWOT, where we do have knowledge of the crop type planted in this area. We do assign for each field for which we have knowledge of the HH minus BB phase inconsistency, the value that we have observed during the SMAPVEX 12 campaign, and that I reported here like in this slide. To simulate the effect of soil moisture, we instead like simulate a ramp over the scene of 15 degrees slope. This means that if we do, we then estimate the ionosphere by computing the difference between an HH and BB interferogram at the same center frequency. For the moment, we do ignore the effect of dispersive scattering, like in this process. We also do also filter the ionospheric phase screen using a weighted Gaussian filter with a filter kernel size of 5 kilometers on the ground. So this simulation pretty much tell us that depending on the type of land cover, we do see that these polarimetric dependent interferometric changes introduce a bias on the ionospheric phase estimate for QQP repeat pass data, which varies between 15 to 90 millimeters. So the magnitude of this change alone is sufficient to break the requirement for NISAR L2 solid art interferometric product, which require to estimate the surface displacement vector with an accuracy better than 2 millimeters per year. So a way to overcome like the presence of polarimetric inconsistencies when using like NISAR QQP mode is to avoid to use the 5 megahertz bandwidth to estimate the ionosphere, but to use and to apply the split spectrum technique on the main range bandwidth of the QQP signal. So the QQP mode for NISAR operates at 20 and 40 megahertz bandwidth. And depending on the width of the range bandwidth, we can achieve different accuracy of the ionospheric phase estimate. Oh, I'm sorry. So in this graph, I just reported the ionospheric phase uncertainty expressed in radians as a function of the interferometric coherence. This is like the orange line represents the uncertainty that we can achieve when we apply the split spectrum technique on the main range bandwidth of 20 megahertz, while in blue we have when we split like the uncertainty that we will achieve when we split like the main range bandwidth of 40 megahertz. And we are comparing the splitting of the main bandwidth with a classical application of the split spectrum technique. So for a dual pole mode, 20 plus 5 and 40 plus 5, where main and sideband are acquired at the same polarization. So in other words, the wider the main range bandwidth, the better the accuracy of the ionospheric phase estimate we can achieve. For example, for the 20 megahertz, so by splitting the main range bandwidth, when the main range bandwidth is 20 megahertz, the ionospheric phase uncertainty is roughly 5.1 times larger than the ionospheric phase uncertainty that we would achieve by applying the split spectrum for a 20 plus 5 megahertz, where main and sideband are acquired at the same polarization. So to summarize, we did find evidence of polarimetric, interferometric phase inconsistencies between interferogram and HH at BB polarization over 12 days. The area that we have analyzed are bare soil and agricultural fields, and we do think that the driver of these changes, in one case for the bare soil, might be soil moisture, while for agricultural field, we do believe that these are driven by changes in the vegetation biomass over vertically oriented vegetation field. It's clear that the magnitude as well the spatial temporal pattern of these HH minus BB interface inconsistency are not well understood, and we cannot exclude that there are other types of land cover which may exhibit these very similar polarimetric inconsistencies. We did simulate the QQP ionospheric phase screen for the Sant Andreas Valley over California, and we have realized that this polarimetric dependent change of the interface may introduce a bias between 15 to 90 millimeter, whose magnitude is sufficient to break the L2 solid art requirement. So our conclusion and recommendation for the NISAR mission is that to avoid biases in the ionospheric phase estimation, we do recommend the use of a dual pole mode to estimate the ionosphere, meaning that use the same polarization on the main and side band. Instead, if NISAR will decide to use a QQP mode, we recommend to adopt a large range bandwidth on the main band, so that applying the split spectrum technique on the main range bandwidth will avoid noise amplification. And we do also recommend the use of the QQP mode on highly coherent mid-latitude region to avoid the absence of ionospheric regularities. And this concludes my talk. Thank you.
Thank you, Virginia. Very clear presentation. We move to our second talk by Masato Furuya. His talk is presenting some other effect that can also spoil the performance of the split spectrum method. And his talk is entitled Troposphere, Dispersive Phase Anomalies During Heavy Rain Detected by L-band INSAR. So,
thank you.
Where is yours?
I cannot share. Oh, yes. Okay. Can you see my screen? Can you hear me?
I can hear you, but I can see the screen not in the presentation mode.
Oh, sorry. Oh, sorry.
In other mode, I don't know how to say.
Yeah, I know. Oh, yeah, now it should be good.
I think it looks good, yeah.
Okay. So let me start. Hello, my name is Masato Furuya. I'm from Hokkaido University. First, I have to acknowledge the co-author, Naofal Sechawan, who has just graduated from master course at our university. And this is basically the result of his thesis. And as you notice, my talk is based not on this satellite, but my talk is based on this EROS-2 L-band satellite. So I think many of you have already know these formulations. split spectrum method allows us to perform dual frequency observations, which can separate the original interface into dispersive and non-dispersive phase. Non-dispersive phase includes water vapor and deformation signals, and the dispersive phase is assumed to come from the first order ionospheric effect. But this is a previous study several years ago. We have applied the split spectrum method to ALOS-1 INSAR acquired during a heavy rain. On the left, you see the rain radar map by Japan Meteorological Agency. As you notice, the rain rate was exceeding 50 millimeter per hour or more in places. And the original interferogram apparently indicates the presence of phase anomalies associated with the huge amount of water vapor. But if we apply the split spectrum method to this interferogram, we will get this. Clearly, the non-dispersive phase is due to the water vapor, but these localized anomalies in dispersive phase are very unlikely due to ionosphere. So actually, there are two interpretations. The first interpretation is a kind of interesting one, which is based on the recent development of high-energy atmospheric physics. Nowadays, it is well known and accepted that high-energy particles like X-ray and gamma ray emitted from thundercloud are detected both in situ by aircraft and on the ground. The X-rays and gamma rays are believed to be emitted from relativistically accelerated runaway electrons. So thundercloud is natural accelerator. And we might be observing those accelerated electrons from as a dispersive interface. The second interpretation is more classical one, dating back to the 1950s or before, but it has not been extensively discussed in INSAR community, to my knowledge. In the literature of GNSS meteorology, Solheim et al. 1999 showed the dispersive effect of heavy rain on GPS based on Oguchi's theory. Heavy rains like these magnitudes will generate non-negligible effect even in L-band. This effect was mentioned in Lamont Hansen's book, but no previous studies have shown the effect from real GNSS data to our knowledge. So we will report two recent heavy rain events using ALOS-2. The first one is on July 31st, 2018 in Kyushu, Japan, where more than 50 millimeter per hour rain rates were observed. And the other date on August 28 apparently includes no rain and was clear day. This is the result of the split spectrum, standard split spectrum. Apparently, most of the broad phase anomalies turn out to be non-dispersive, which makes sense. Dispersive phase is mostly flat, as we expected, but we can notice some very localized phase anomalies, where we can similarly observe large and localized anomalies in the non-dispersive phase as well. Incidentally, the original bandwidth of the SAR data is 79.4 megahertz, and in this case, the new bandwidth is 16 megahertz. This is the second case in Shikoku, August 15, 2018. Again, the rain rate was exceeding 50 millimeter per hour at the time of SAR imaging. These are the result of standard SSM from left to the right. Original interferogram, non-dispersive phase, and dispersive phase. We do not have applied any filters on both the non-dispersive and dispersive phases. In view of the rain radar map here, the anomalies here apparently corresponds to the rain radar map and correspond to the heavy rain. And we can notice anomalous phase both in non-dispersive and dispersive phase at the same location. And presumably, I think these long wavelengths phase trend is probably coming from ionosphere, but these are probably from heavy rain. By the way, the effective spatial resolution of these images is about 30 to 50 meters after multi-looking. But we have confirmed that there was no problem in coherence, and that's so we could easily unwrap the original interference. So from now, we first address the question, try to answer the question: is the dispersive phase anomaly due to runaway electron avalanche or rain dispersive effect? So before moving on, we have checked the status of ionosphere at the time of data acquisition using both ionosonde and GNSS ROTI, rate of TEC index map from Japanese GNSS network. We have confirmed that the ionosphere was very, very calm at the time of psi imaging. So next we examine the lightning data and ground-based rain gauge data in Kyushu. Lightning data is from Japan Lightning Detection Network, and it turns out there occurred only one lightning, but it was outside the psi imaging area, and also the occurrence was 17 minutes after the psi imaging. So lightning did not occur during the imaging. On the right is the distribution of JMA's ground-based rain gauge network and the time series of 10 minutes rainfall at several stations. In terms of the spatial and temporal locations, the rain effect seems to be detected in the image. Next is the lightning data in Shikoku. In this case, there occurred 11 lightning episodes near the heavy rain area here. Moreover, but a little bit shifted to the west. And moreover, they occurred 15 minutes before the psi imaging. Therefore, lightning did not correlate with the dispersive phase in terms of the spatial and temporal locations. We thus rule out the possible effect of runaway electron avalanche. And this is the ground-based rain gauge data in Shikoku. Luckily, this station, 74391, was exactly located here and showing 15 millimeter rain per 10 minutes. So the rain gauge data shows very good correlation. So we think that these non-dispersive phases are presumably coming from troposphere, not from runaway electron avalanche. And in order to isolate the effect of heavy rain from the first order ionospheric effect, we need to add another dispersive phase term, like the higher order ionospheric effect. Because, however, we do not yet know the explicit functional form of this another dispersive phase. So we just set it as X as a function of frequency. Although the exact form of XF is not available yet, we can at least mathematically isolate another dispersive phase following some algebra like these. But first, subtracting these two equations, we will get this. By the way, we set the third frequency as the original center frequency. So we can derive these two equations, and after some algebra, we will arrive this final form. Although, anyway, these yellow color highlighted gamma delta F and gamma delta F prime can be derived from the previous triple frequency formulations, and but we do not know the exact form of these function YF, but we can evaluate the order of magnitude by simply dividing this gamma delta AF prime minus gamma delta AF by 10 to the power of 9 Hertz. And this is the result of proposed formulation. And we also performed this analysis using the fair weather images. So comparing these, this is Kyushu case, and this is the Shikoku case. So we can conclude that another dispersive phase does exist during heavy rain. These phases could be derived from the previous formulation. And in order to quantify the rain dispersive phase, we have compared the magnitude of phase anomalies as a function of rain rate. We categorized each pixel value of rain rate data into 6 to 7 classes. Then we picked up phase values at each categorized pixel to compute the root mean square amplitude so that we can check if they are correlated or not. And these are the comparison of raindrop phase and water vapor phase as a function of rain rate. Overall, we confirm that we confirm positive correlation between both phase anomalies and rain rate. And this is another application of the triple frequency measurement. In 2017, we inferred high R order ionospheric phase from dual frequency data using minimum norm approach. On the right is the result of another dispersive phase from the triple frequency formulation. We think these phase changes are significantly different from zero, and this would be an independent confirmation of the presence of higher order ionospheric phase. So in summary, in the heavy rain inside images, standard split spectral method delivers significant anomalies, both in non-dispersive phase and dispersive phase. And comparison of with the ground-based lighting data and rain gauge data, we prefer, raindrop dispersive effect is much more likely. And our formulation demonstrates that another dispersive phase does exist during heavy rain. And the RMS amplitude of these another dispersive phase and non-dispersive phase and rain rate show positive correlation. The another dispersive phase effect is on the same order of magnitude as the higher order ionospheric effect. And finally, this is my take-home message. C-band and X-band INSA should be better at detecting raindrop dispersive effect because they are less affected by ionosphere, and also they should be more sensitive to rain droplet. Thank you.
Thank you very much. Very, very interesting. I keep some questions for later. We can move to the next speaker, Christoph Giesinger. And the presentation, his presentation is about the enhanced timing annotation dataset, this new product. Yes, I can already, your presentation is coming, so please start.
Yeah, thanks, Francesco. So, hello everyone. I would like to give you now a brief introduction about the new ESA extended timing annotation dataset, which was also briefly mentioned in yesterday's plenary session. So, I want to show you what we've cooked up here and give you some ideas on what we did for the validation. So, before I start, I want to acknowledge my co-authors, which are from DLR, from ESA, Norse, PPO Labs, and also from NVO, who helped us in the validation process. Okay, quickly on the motivation. So the basic idea behind this product is that you see here the geometric product specification from Sentinel-1, which is on the order of a few meters, which is very good for the classical SAR imagery. But we all know from research in the previous years that we can go much deeper into the subpixel level and even to centimetric level. And the idea of this product is to make this as easy as possible for the user without compromising in quality. So we want to provide them corrections for all these atmospheric disturbances, for tidal effects, and also for some effects specifically related to Sentinel-1. You can see here our formal goal is to get on the order of 0.2 meters with range and 0.1 meter with azimuth. So these are primary product specification. I will also show you some practical results where we can usually do better than our boundary condition here. And the important thing is now this product will be generated operationally, hopefully in future, for all the data that's occurred over land. So this means strip map data and IW data for now, but we already prepared for EW data. So we will hopefully give you then the full package in future. Okay, quickly on the key features. So we cover the whole data takes with this product. And the important thing really is the net CDF here embedded in this safe product structure, which gives you all the information for applying the product. So no need in principle to dive into any additional annotations. The net CDF gives you all the information. And we also provide the precise orbit solution, which is of course crucial to get the best out of geometric SAR. It's completely tied to the SLC product. So you have temporal coverage and the SLC ID here to cross-match the product and the original SAR data. We have a KMC preview file, which I will show later in the presentation. And the basic information is already prepared as gridded slant range and azimuth information corresponding to about 200 meter resolution. So the only goal here is to upsample this to do the correction. And timeliness is around 21 days, which is simply because of the precise orbit solution. Now, to do all this on a global scale, we need really a highly efficient processor. So we need to work on the methods that it works everywhere, as reliable as we can do it. We need to get the background data, and we need to really get a high throughput to keep pace with Sentinel. So this led to our so-called CTAP IPF. Now, this processor would be a talk on its own. Here I have to be brief. So in a nutshell, we are getting external data here from ECMWF, operational data here for meteorological 4D data as inputs. We also gather the electronic content information from the IGS services. And we have the in-house data from Sentinel, the precise orbit and product annotations, which are fed into the processor over here. Which has access to the Copernicus 90-meter dam as a resource. So this is one of the most precise DMs available at the moment, so which we use as our background for consistent information. And we use ephemeris data here from JPL for the tidal computations. And this all goes into the processor. You see here some of the sources. So this is all based on previous research we did. And out of the processor, then comes the ETAT product with the correction information. And here a rough number to get an idea of our throughput. So for all the steps we have to perform here to get all these corrections and data preparations, it takes around 65 seconds for a typical IW slice. So we're on the order of a few minutes for regular Sentinel-1 data takes. Okay, so here's the core of the product, which is the net CDF. Yeah, you can see here on the left, it's really replicating the SLC structure in that sense that we have the different IW swathes here in the case of the IWs. And then we have the burst level, and at the burst level, you can find all the different grids that are necessary to correct the products. And there's also annotation information, most important, let's say magic numbers, which are calibrating the instrument with respect to our product. And the principal application is straightforward. So everything is annotated in range and azimuth grids. It's in seconds. So you pick your favorite layers. The easiest thing, of course, is we provide you with the sum layers. So in principle, you only have to use the sum in range and sum in azimuth to get all the information in one layer, but you can also pick your favorite ones if you want to. And then you identify the bursts from ETAT and SLC. You upsample from the bit coarser resolution to full SLC resolution. You subtract the information, and then you may or may not resample the SLC, and then you have the corrected SAR image, which is hopefully good at the centimetric level. Quickly on the preview files, you can see here one example. So these are really long data takes, in occasion some 15, 20 minutes crossing whole Europe. You see here we have the full data take footprint. We see here a bit the burst level, which we actually annotate in the net CDF. We only have the sum layer. We do not annotate all of them in the KMC, only the sum layer, but we give you an idea of that. What is happening at the location. So you can see here also, usually it's metric total cumulative effects in the range, and maybe some -5, 6 to meter level here in the azimuth. We also give a bit of a pop-up information if one clicks on this slide, on these bursts here. You can see here the different information for the background SAR product, what is the start and stop time, and so on. So you can see here all the sum of these individual layers here gives you this cumulative effects shown here. Okay, now the question is, how good does this work in practice? We have calculated already quite a substantial amount of test product at different locations, and one of our methods to check quality is to do a geolocation analysis, which is based on the idea that we know reference targets on the Earth's surface. We can compute reference azimuth and range times using the precise orbit, and this we compare with what we get from the embedded information of the SAR image. And we only have to apply here then the sum layers of our ETAT product to see if these two things match. In principle, we would expect 0. And we just use here conversion factors. Actually, it seems I've missed here a C-half, so to convert it here to units of length. Okay, so if we do that, you can see here on the left side, this is the result if we don't do anything. So this is the usual result we see for Sentinel-1 IW data. We have effects related. So some of these reflectors happen to be in burst or swath overlaps. So we see distortions here coming from systematic effects. Also the tropospheric offset here. So if you apply then the ETAT product, you can see everything comes nicely together. So for the range, we don't have to bother at all now. We are quite within our budget of 20 centimeters, so even at a few centimeter level here. And for azimuth, I want to point out this small, let's say, disclaimer we put on our quality, which is the product itself. So we have to take into account, of course, the target signal to clutter and so on. So with the 20-meter resolution IW, of course, we cannot expect much more than having a few DC meters here. So this we don't attribute to our product, but to the Sentinel, let's say, background data. And that it's indeed the case, I can show you here with some strip map data. ESA thankfully acquired a full stack here for 1 year for strip map in the Australian side. So we see here again before, we see the usual offset here in the azimuth coming from bistatic effects and tropospheric effects here in range. If you apply the correction, everything gets very nicely together. We see only very small centrometric numbers here for the strip map data. So this is very, very good. We also see here the spread in azimuth. This is where we want it. We have here still a small offset here in the strip map data, which is because we have now so far that, let's say, the magic calibration numbers, they have been adjusted for IW data, and we definitely have to do this a bit more careful than for the strip map data to make everything centered. Okay, final part here is then the validation, let's say, in some of the applications. So we teamed up with NVO here because they do this nice regular service of feature tracking of ice velocity in Greenland. And usually they have to do quite of a substantial correction and mitigation process to get rid of spurious signals that are introduced by troposphere and ionosphere. So usually they use stable terrain to stable their movement data where there is none. So with ETAT, we hope we can get rid of this calibration and correction step of this empirical one, and by simply apply the correction, make sure that everything is right where we want it from the very beginning. So we have, NVO has a very robust multi-annual result of Greenland that we can use as a reference, and we compare this with some of the test data we computed for specific data takes here over the Greenland ice sheet. So we picked here for the demonstration, we picked here this track 31. And we also did, by the way, this analysis for the Iceland data, but this is not shown here for the given time here. It's a bit too short to go into all the details. Okay, so for the line of sight, the feature tracking results here. So on the left, you can see the multi-annual reference map. In the middle, you can see this pair that we picked here for, this is a 6-day pair with Sentinel-1A and 1B. And if we don't do anything and just do the feature tracking between the two acquisitions, we can see here a lot of bias and signals in between that are coming from differences between S1A and S1B. If one would look closer, one could also see here features coming in the topography area here at the coastal range. And if we apply the ETAT, we can see here that we are already very close now to the multi-annual reference. It's a bit noisier, of course. It's only one pair here, but we see here that we definitely do something right if we apply this product. Okay, for the long track, same here. Of course, this is more difficult because we have the much coarser pixels. You can see here the uncorrected effect here between S1A and S1B. If we apply the corrections again, we get much closer here to the annual reference. We have some differences here. This is the IW1 subswath. We are pretty sure that we know about this. This is one of these antenna events for the Sentinel-1A that is known to have changed some of the features here or the characteristics of the IW1 beam. We have not yet accommodated this in our ETAT product, but in principle we can do this, and I think on the long run also ESA will make sure that such things are also captured here by our correction product. Okay, some statistics here with the details. So the multi-annual reference can be checked against our corrected results, and we can take the histograms of all these different pixels. So NVO made here the statistics, and we can see mainly here that we have the bias correction for the 6 days pairs. So data what is previously offsetted here by several meter per day velocity, artificial velocity is now corrected and much more close to 0. As you can see here also with the average results here. We also do this, of course, for the 12 days examples that we have. But due to the normalization here, when we have more days in between already, the impact, of course, by the spurious signals, they get smaller, but we can still see here the impact. Okay, and finally, the second topic, which is also more, let's say, ambitious one. So the product is not necessarily tied to interferometry, but it can be, of course, used to estimate atmospheric phase screens from all our layers. So we want to look if we can do something about the long wavelength effects across interferograms and also about the stratification effects that we have in the topographic areas stemming from the troposphere. So for this, PPO Labs received a stack of 12 ETAT products, which corresponds here to a stack in Norway region with a lot of topography and fjords and so on. And they had a look if we can do something by converting the ETAT into a atmospheric correction. So here on the bottom, you can see in a nutshell what is to be done here. So it's very simple and also very close to what we do with the standard SLC. So we apply co-registration to the ETAT layers that are sampled to SLC resolution. Then we just rearrange the different components here for their correct signs. So prominently, of course, the ionosphere has to be inversed here from delay to phase correction. And this information then can be converted into a phase information and subtracted again from the interferograms. And so in the center here, you see one of these very nice, smooth, consistent correction patterns derived from ETAT. And if they are applied here to the original interferogram, you can see that fringes that move here across the whole swath here of Sentinel-1 are very well removed here by the corrected and compensated interferogram. And the second information is on the stratification here. So a close-up here on one of the regions here where we have fjord and mountain valley situation. So we can also see again the previous situation before doing anything. So this is around 1.2 fringes per kilometer signal moving around here in this mountainous area. And if we apply the ETAT here, the information is quite removed here. And we see hopefully more useful signals. So an evaluation is still ongoing, but I think this is quite promising as a start. Okay, coming to the conclusions here. So we have now developed in 2 years of intensive work with ESA, we have developed this product that provides all these well-known effects in SAR in a user-friendly and very application-ready package. We have validated the product at the reference sites with corner reflectors, which shows that we are doing very good here. NVO has analyzed the first set of data sets in the feature tracking application, and they are now quite convinced that this will help especially on the large ice sheet areas like Greenland or Antarctica, where we have no other way to stable the reference data or have stable topography to do a correction, so that we can do this with this product now more efficiently. And the PPO labs, they're also quite happy with the first results here. What they see in their different interferograms, that in most cases the ETAD is really helping and is not, let's say, introduce new distortions. Only very few, let's say, localized features are sometimes missed, and on occasions there are stratifications introduced, but this occurred really only in a very few of these test compares that we analyzed. Now, to summarize a bit the outlook here on the ETAD roadmap. So now here we are at FRINGE, and we think now that what we have at the moment is maybe at that, let's say, demo product status. We have delivered the processor to ESA. It's fully integrated, at least in the GAP platform, where it can be accessed to users now for own evaluation if you contact ESA about this. ESA is also very active now in building up user documentation and information on the product. So we have a Python API that shows more details on how to apply the product, gives you sample code on how to access the NetCDF and so on. There is now documentation just recently now put on the Sentinel webpage that gives you now links to background documentation of the product. So this is in the, let's say, the first task that ESA is now working here in 2021 to get the product known and have it in a more demo product status. And on the long run, of course, we hope to have this as a core product and in the regular operational processing. This is still pending at the moment because of the budget decision that was explained yesterday also in the plenary session. But we hope we can move this forward then by 2022. And if you're interested then about this product, if you want to look into this, please contact us or Sentinel-1 Mission Manager. Okay, so this was it from my side. Thank you,
Christoph. I think we move directly to Heresh, to his presentation on the impact of ionospheric range delay on the geolocation of low-frequency SAR data, implications for NISA.
Sure.
I think you see the wrong view.
Okay, let me fix it. All right, is that good?
No, I think it's not. We see some presenter's view, like.
Oh, okay, then let me change it back. Is this fine?
This is fine. This is fine.
Okay, okay, great.
Go on.
All right. Hello, everyone. I'm going to talk about a topic very similar to the previous presentation. But I believe the geolocation for low frequency SAR is going to be a little bit more difficult. So, and the main reason really is going to be ionosphere. I would like to thank my colleagues, especially Yunjun Zhang and Xiaoqing Pi, who have done a lot on this project. When we talk about geolocation, of course, we have the SAR data in a range Doppler coordinate system, and for many reasons, we want to label each sample with a geographic location. It could be just because we want to co-register a pair or a stack of SAR data for time series analysis. So any time series analysis that we are doing, if the stack is not aligned, that's gonna make our life difficult and introduce a lot of errors. So we really like this co-registration alignment or geolocation be done in a closed loop with geometrical information. In theory, it can be done. We can just use metadata and basically achieve some geolocation. The nice thing about that is if we have a stack already existing and a new acquisition comes in, we just need metadata. We don't need to go back to the previous acquisitions and do any refinement. So the data system is going to be very simple. It's going to be less compute needs and less expensive. However, if we, for some reasons, as you will see
in future slides, if we need to do some data refinement, then the system is going to be a little bit more complicated and it's going to be expensive. So the question is really, can we always use geometrical geolocation? To answer that, we had to go back to the basics and look at different contributors to the geolocation. And specifically in this presentation, I'm going to talk about range direction of the geolocation. So we have atmosphere with ionosphere and troposphere. Ionosphere is going to have a larger effect on the low frequency, tens of meters in L and P band, troposphere 2-3 meters with tens of centimeter variation. We have orbital errors around 1-2 centimeters. Orbits are good these days. And we have ground surface motion, solid earth tide, other kinds of tides, and even some loading. Ionosphere is very important for us because at JPL we are working on NICER, as I said, and the radar at JPL site is really L-band. So this plot shows how the slant range delay looks like on the y-axis on the left versus the vertical tech on the x-axis. The blue plot basically is the range delay due to the ionosphere for the L-band. And as you see, for example, if we look at 20 TQ, we see already around 7 meters delay in L-band, while in C-band probably we are at few centimeter delay. So 7 meters delay is a lot for not much tech. 20 TQ is not much actually. We could reach significantly larger depending on the daytime and also seasons, solar cycle, all those things. But 7 meters is already 1 pixel in our 20 megahertz data. So it's important. We know that our data is going to be on orbits very similar to Sentinel-1, 6 a.m. and 6 p.m. local time. At 6 a.m., usually ionosphere is lower and the variation is lower. So, so perhaps we will be most likely fine, depending on what's the definition of fine. But at 6 p.m., the tech variation is going to be large and the tech itself is large. So we won't be fine just by doing nothing. We took a stack of L-band data from ALOS-2 and we did geometrical co-registration of the stack of around 50 acquisitions. And then we looked at the residual geolocation errors by cross-correlating the stack and doing a time series. And here in the top plot, I'm showing the time series of the range delay or range geolocation errors, which is the blue plot. And the variation, as you see, is around 10-12 meters at the beginning, where it is closer to the last solar maxima around 2014, 2015. And then by time it gets down, we took ionospheric products from IGS, which is every 2 hours, and we already got some good match with what we had in what we observed in the SAR data. So indicating that really, as we would expect anyways, the main source of the delay is ionosphere. But then we got some in-house, more precise tech at JPL based on GNSS data. At least we tried to get the tech data exactly at the same time of the SAR acquisitions. So that improved the prediction of the range delay. However, so this was a significant improvement. We got down from 10-12 meters of the geolocation errors to 1-2 meters. If we look at the residual, which now is the blue. And if we look at other sources for this L-band data set, we looked at solid earth tide, which usually after ionosphere, you would look at solid earth tide. And we see still we are too far from solid earth tide. And 1-2 meters, we thought it's still ionosphere. So what it could be. We got GNSS tech data from GNSS colleagues that they usually take. We have receivers on the ground, and GNSS satellites are at altitudes around 20,000 kilometers. But our SAR sensors actually are at orbits around 700, 800 kilometers. That's the case for Sentinel-1, and that's the case for NISAR will be. So what we are getting is the total tech from ground all the way to 20,000 kilometers roughly. But what we need really is up to 750 kilometers, 800 kilometers. So we need really to remove this part, which we call the topside tech or above orbit tech. We don't need that. That doesn't affect the SAR data. To understand the impact of the above orbit tech, we use GNSS receivers from Sentinel-1 platforms, thanks to ESA, that actually provides this data freely. We could estimate tech from GNSS receivers on board the Sentinel-1 A and B platforms. Actually, Sentinel-2 has the same data, but we looked only at Sentinel-1. And that allows us to actually subtract the topside tech from the total tech and get to the suborbital. We did that, and on the left, we see the tech products as they are provided generally, but here we got it only for this exact SAR acquisition time. Here we are showing for one specific cycle of Sentinel-1. On the top left is total tech, on the top right is the above orbit tech, which goes up to 12 TQ, which is not really negligible. And then on the bottom, we see the difference of the two. We had a stack over Chile, where we know that the tech is high and the variation is high, so we would see some signals in the even C-band data. And we had the topside tech and the total tech, so we looked at some analysis. My colleague Yunjun did. This is a nice plot that shows the stack of more than 120, 30 acquisitions over Chile, that we see a nice seasonal variation. We see that over the years closer to the last solar maxima, which was 2014-15, we see around 20% of the tech, total tech, was due to the topside tech. Of course, as we get to the solar minima, the percentage is even higher, but of course, just note that the total tech is low anyway in the solar minima. So we took that stack over Chile and we looked at, we co-registered, it's a deep stack, and then stops data, and looked at the misregistration in range direction using the cross-correlation pixel tracking. And that would be the blue plot. Then we estimated, predicted basically kind of the range delay from ionosphere without accounting for the topside tech and after accounting for the topside tech. For the C-band data, first of all, it's very obvious that really ionosphere is dominating the observed range delay in this region, even though it's C-band, but we clearly see that how heavily affected by ionosphere because of the region. We don't necessarily see very clearly the impact of the topside tech because it is C-band, but that's not going to be the case for our L-band mission. After accounting for ionosphere, we looked at a little bit more details, and we see very clear tropospheric signals, as also discussed in the previous presentation. Here is an example, the DM of the region. We have like 4 kilometer elevation change, and you see the range offsets after accounting for ionosphere. And on the right, the tropospheric delay from era 5. So very obvious that we have troposphere there contributing. After accounting for ionosphere, we have this residual in blue. And then if we predict the tropospheric delay, we see after 2017, very nicely, the seasonal delay is dead. After accounting for troposphere and ionosphere, then the residual is very clearly dominated by the solid Earth tide, which all those ups and downs are due to the solid Earth tide. So here is the, since we were interested to see the impact on the NISAR, we basically took those tech data, the total tech, suborbital tech, and top orbital tech and scaled it to L-band, S-band, and C-band. And one very important lesson for us on the NICER mission is the top orbital tech cannot be easily ignored because around 10, 12 TQ actually gets us to 2-4 meters range geolocation error or range delay. So it's not small anymore for us, even though it might be small for C-band. We looked at another stack over what I showed you for Sentinel-1 was 6 p.m., which we know ionosphere is high. We looked at 6 a.m. stack. And here I'm showing the RMSE for the range offsets after just geometrical geolocations. And then as we correct for tech using IGS and then using our tech at JPL, and then after correcting for solid earth tide, and then after correcting for tropospheric delay. There is one outlier in this data set that we believe is something related to the data, not related to ionosphere or environmental effects. But if we exclude that, I think the residuals are in the order of 6-7 centimeters after all corrections. And if we scale them, actually we get to around 1 meters for L-band, which is consistent with what we saw also in ALOS-2 datasets, which was L-band anyways. The results were so actually impressive to us that we thought, okay, maybe it's time to go back to see if we can measure tectonic signals using pixel tracking. So we know that in the past, pixel tracking has been widely used to estimate large displacement. My colleague Yoon-Jun Zhang had a presentation yesterday that he explored this data set over San Andreas Fault, and after some corrections, basically we see the tectonic signals, which is around 1.5 centimeter per year. So this is really promising. In conclusion, I think, I hope that it is clear that ionosphere is gonna be our major issue for geolocation errors for L-band, no surprise. But with some corrections, we might be able to get down to 1-2 meters in range direction. I believe for many applications, C-band is fine just with geometrical approach, but with the what you saw from the previous talk, I personally am very excited to explore that more, and we can get even better geolocation errors. So basically, I don't think if we really need in many areas to go to data-driven geolocation or refinement. But for L-band, it's a bigger problem. If we don't do anything, we get tens of meters delay and geolocation errors in range. So we need to really take care of it, and we have to be prepared for it. That's it. Thank you for your attention.
Yeah, thank you, Haresh. Our next talk is given by Bettina Kam, and the title is Upgrading the Zero-Mean Assumption to Infer Absolute Zenith Delays from Double Differential Interferometric Observations. Yeah, I think your presentation is coming.
Perfect. So welcome to my presentation. I will tell you about my method to upgrade the zero-mean assumption to infer absolute Zenith wealth delays from double differential interferometric observations. In the project I'm working on, the Atmo Water project, we want to develop and evaluate new approaches to derive improved spatial temporal estimates of the atmospheric water vapor distribution. So instead of seeing the atmospheric water vapor as a error source in INSAR data, I want to really detect it and get a good signal out of it. So we use SAR, Sentinel-1 satellites, and other project partners use GNSS to calculate integrated water vapor. And we do an approach of using those in a tomographic way and in a data fusion approach for weather model data. So that is our area where we are interested in. In blue, that's the area where I'm using SAR scenes, and you see in blue and red the dots are the GNSS stations. So we have a better spatial resolution, of course, for INSAR, and that's the advantage we want to get out of the INSAR data. And in green, you already see our validation stations. So how am I processing my data? I processed 169 Sentinel-1 scenes from 2015 to 2019. I don't want to focus on the basic processing, the PSI processing. I use snap and stamps for that. So I will start here now with the unwrapped phases, which where I estimate and subtract the linear deformation, and I get unwrapped phases which are deformation corrected. Next, I'm mapping those slant delays to the zenith direction, and I apply the standard zero mean assumption, which is commonly used. Afterwards, that's the block of my methods where I will explain in a moment. And finally, we transform those zenith wet delays to integrated water vapor, which is the water vapor product the meteorologists are interested in. For that, for the upgrade of the zero mean assumption, I need additional input to calculate it. So I'm using ERA5 grid data. So that's the latest ECMWF model data. I interpolate it and I calculate zenith wet delays at each PS location and also time step. So I can calculate means or also a describing function. I will focus on that in a moment. And finally, for transformation, I also need ERA5 for the mean temperature. So let's focus first on this part of ERA5 data processing, as it might be new to many of you. So I have the ERA5 grid is an hourly data on a 0.1 degree fine spatial grid, and it is given on pressure levels. So the parameters I use are the specific humidity, temperature, pressure, geopotential. First, I use the approach by Wang et al. 2015 to do a vertical inter and extrapolation so that I have really for the heights of my PS points the grid cells, and I do a horizontal interpolation to get also the finer resolution of my SAR data. There I use the approach by Jade and Jian 2008. Afterwards, I calculate the wet reflectivity and mean temperature and integrate it to get the zenith wet delays from my PS point to the top of the atmosphere or of the model. So the zero mean assumption is hidden behind this IPS inversion. So we have an underdetermined problem to get from the interferograms to phase screens for each scene. So we need an additional assumption. And commonly it is used that in the mean, the atmosphere will be constant over time. So my first question is now, how valid is this zero mean assumption? And for that, I calculated, as stated before, from the ERA5 data, zenith wet delays, and I summed it, calculated the mean over my whole set of scenes, so over the 169 time steps. And if I calculate the mean, the true mean will look like that on the right-hand side. So you see values varying between 90 and 114. So the next question is all this now due to topography? Because the people who know the Upper Rhine Valley will see the Upper Rhine Valley on the right-hand side. So I calculated the deviations due to topography. On the right-hand side, you see the topography. On the left-hand side, the height and the mean zenith wet delay from my ERA 5 data. So you clearly see a functional dependency, but it doesn't explain everything. So if I use this calculated function and subtract it from my mean zenith wet delay, I get on the right-hand side this residual delays which are not explained by the topography. So it's ranging from -3 to +3 millimeters still. So in the mean over 169 scenes, that is a substantial difference. And the reason is one reason is that there are just regional effects of higher water vapor in the atmosphere. Now I also calculated the mean for different stacks. So if I only take the year 2017, I have 59 scenes, or 2018, I have 47 scenes. And of course, the range is very similar, but you can see different characteristics. 2017, for example, on the northern part, there are higher values than in 2018. So it is really important that you calculate the true mean for your specific stack and not just take a mean over a long time period and you have only a substack of that. So now we do this mean correction. So I showed you how I calculate the true mean for my INSA stack, and I do this correction. I correct, instead of using the 0 per pixel or per PS point, I use now the mean correction for the onto the atmospheric phase screens. And you can see an example from 2016 in April. On the left-hand side, you start with the zenith partial wet delays coming from the APS inversion. And on the right-hand side, it's the mean corrected data using the ERA 5 mean values. A next part is this correction of a low frequency part of the atmosphere. I hesitated to just subtract all RAMs or anything because atmospheric signals look often very much like those RAMs. And as I'm interested in the whole atmospheric signal, I can't just subtract all remaining signals. So I'm using the ERA 5 data to calculate the low frequency part of the atmospheric signal. In my case, for this area, I use a polynomial of second degree, but you could also think of, if you have a smaller area, to use just the linear, a linear function to correct, or for bigger, you could think of another function. Here, I used the polynomial of second degree. So how does this work? On the left-hand side, you see for the date I showed before, again, the mean corrected PSI zenith wet delay. And in the middle, you can see the low frequency estimation onto this difference between ERA 5 and the PSI zenith wet delay. So here I clearly have a ramp going from south to, or down from the south to the northern part. And this is really something I can correct. So I correct this describing function to my SAR data, and I get a final zenith wet delay where I correct all these elements from my ERA 5, using my ERA 5 data. And just to show you that a linear function doesn't describe always the full picture, here you can see in the middle that has clearly a kind of quadratic contribution in it. It's not a ramp, but it is important to correct it from the left-hand side where you see the not corrected to right-hand side where you see the corrected values. Now I showed you how the block of my methods where I implement it and how it works. Now I need to somehow see if my results are valid. So for the validation, I use the GNSS data provided by my colleague Pong Yuan, who calculates the GNSS integrated water vapor for the project. And I will now concentrate on some stations which are in my area of my source scenes, and especially on the 5 stations which are marked here. So, for example, if I take the validation station from Montbéliard, you can see the difference from the GNSS to the SAR data on the left-hand side. And the difference is quite spread, and we have a small bias, so we don't have the systematic errors visible here, or no big errors at least. And on the right-hand side, I use the normalization to normalize it on the integrated water vapor value, the difference. So there we have a very small bias of below 1%. And finally, we can also look at the validation at one data point in time. So it's again the April 2016, and you see all the stations on the x-axis, all the GNSS stations. And if I calculate a difference of the 10 nearest SAR points to this GNSS value, I get this difference in integrated water vapor. If I do that for all time steps, I get a mean bias for all the stations of 0.1 kilogram per square meter integrated water vapor, and I have a standard deviation of 1.2. So to sum up those statistical values, on the top in green, you see the validation stations with the reference value of the mean GNSS integrated water vapor. So it's ranging between 16 and 19 kilogram per square meter. We have a bias per station where clearly the Fribourg station has a much higher bias than the others, and the CHRM station has a higher standard deviation. And I looked at the standard deviation of the 10 closest points to each GNSS station, and those are very consistent to each other. So they have an inner precision of 0.2 to 0.3 kilogram per square meter. So the SAR data around those GNSS stations is consistent in itself. And below you see the validation stations, so the mean bias over all GNSS stations and validation stations. And you can see that the relative bias is at 1 to 2.3% of the integrated water vapor. So in summary, I used the method to upgrade the zero mean assumption, which which has a height dependency correction in it, considers regional characteristics and seasonal effects on the stack, and we do a low frequency correction considering also weather phenomena which are produced at this time steps, and we did a validation using the GNSS stations. Thank you for your attention.
Thank you, Bettina. I think we are late, but I guess we can still do a round of questions. Maybe we can start from Virginia. From myself, I see there's no recommendation for ESA for this, apart from don't do the quasi-quadrupole, right? I've seen in the chat there is something for you. Yeser Maksudi says, when using the phi CP, which I guess is cross-pole, how would you take the scattering behavior difference in the two polarization channels into account?
I think he's referring to the difference between an HH and BV interferogram, which automatically takes into account the differences in the scattering behavior. Just to rephrase it, when we form an interferogram between a reference and a secondary SLC at a fixed polarization, we can decompose it in the superposition of different contributions like topography, ionosphere, atmosphere. So these changes that we see, we think that they might be attributed to changes in the scattering phase. So when we form the difference between an HH and BV interferogram, all the polarimetric independent contributions like topography, ionosphere, and troposphere, they cancel out, and what remains are changes in the scattering phase, which we think might be attributed to soil moisture and vegetation biomass. I hope this answered the question.
Since we don't have the speaker, the audience live, so it's I would then ask something to Masato. I think I found your presentation very interesting, and I was wondering. So I think if I interpret correctly, you demonstrate we have some additional differential dispersive effect in the data. This is clear, and we are asking ourselves what it is. And I was wondering if it could be also some moisture effect on the ground, causing some dispersivity. Maybe like this decoupling as usual can happen, the group delay from the phase delay somehow. Have you thought about this, or what do you think? Is it crazy or?
Yeah, I understand your question, but I think after the split spectrum method, the anomalies only appears around the heavy rain area. The areas outside are also wet, should be wet. So yeah, maybe it's possible that the soil moisture can somehow gives rise to dispersive effect. Yeah, it may be possible, but I think it's as I showed in the previous former study by Solheim et al., they introduced the frequency dependence of the phase even in L-band, in GNSS. During the heavy rain, it's basically the elementary physics is basically the forward scattering of microwave. It gives rise to some different phase amount depending on the frequency difference. So I think personally it's unlikely, but maybe true. I don't know.
I think maybe if we look as you were suggesting at higher frequencies like X-band or C-band, then maybe this is a good experiment because maybe we expect to see this phenomenon enhanced and the other maybe not so prominent. Yeah, maybe you suggested something. Maybe to Christoph, I've seen one request to provide the links for the ETAD products. I guess people can also contact you and you can give details about when and where this will be available.
Yes, I think so.
By Richard, it says, nice presentation. Do you use VMF or ERA5 for tropo delay? It was interesting to see the stratification in APS collection despite the low resolution.
Yes, so just quickly on the link. So it's already partly available on the Sentinel Copernicus webpage. So if you search there for ETAD, you will find the starting information how to access this, let's say, product at the demo level. Now, coming to the question about VMF, so this is the Vienna mapping function approach or the ERA data. So I was very quick on this. So what we do here, we use the operational integrated forecast data. So we don't do reanalysis data, but we use the operational data that becomes available usually one day after the model has been finally updated or converged to this, let's say, best knowledge of the atmospheric state. And this data set also has quite a good resolution on the order of, let's say, 10 by 10 kilometers. And so this is what we use here to really do the integration of the full meteorological information, 4D information. So time is also involved, of course, to calculate all this sample points we use in our grid for the tropospheric effects. So I think by this and by the DM that we have in the background, I think we can capture most of the stratification that is coming from topography and model information.
Yeah, thank you, Christoph. I don't see questions to Haresh. I maybe have one myself about. We were playing with Giorgio with absolute ionosphere, trying to get the absolute phase and absolute ionosphere. What do you think about this? Is it going to help in L-band to solve some of the challenges in the geolocation? Are tying an entire stack properly, then we have just to solve for one single offset or things like this. What do you think? Have you ever thought about this?
You mean getting the ionospheric phase estimate from split spectrum and then use that for the geolocation? Is that what you mean?
I was thinking if we like using, we were suggesting something, I think at the user conference, like using 3 bands, or maybe it was also before us, using 3 bands and trying to get some absolute differential ionospheric phase between pairs, so that you tie somehow the offsets internally in the stack so that they are all fixed. If you ever thought about this, or what's your opinion about this? If this is because we tried, it's hard because there's a lot of systematic errors and problems. I don't know if it's easy, but
no, not much on the absolute ionospheric phase. I haven't tried really, but one thing to consider is really not all these SAR products are interferometry products or interferometry time series products. So, we have products that one SLC comes in and one SAR image derived product goes out. So for those applications, we need still to precisely geolocate, and we don't have access to pairs or doing interferometry.
Yeah.
So I think the favorable approach would be really to, if we could have a closed loop solution, that would be the best solution. That's why they still try to get the geometry to work. That's why I think Christoph is trying to have some metadata helping with geometry to work.
Yeah, thanks. I don't know for Bettina if we do have questions. Yes, there's some question asking, aren't you introducing the atmospheric bias by subtracting the ERA 5 mean ZWS zenith delays, I guess, from the PS points?
Yeah, so I checked that. I also looked at the difference between my ERA 5 zenith wet delays in comparison to the GNSS wet delays, also using the zenith wet delay at the PS point location. And there I didn't have this bias, or I had a much smaller bias, so it's not introduced by the ERA 5 data. Yeah.
Thanks. There's also a second question, I guess, still for you. Can you see it?
Yeah. Shouldn't we model delay due to pressure differences and not only use zenith wet delay? Yes, that would also be an idea, but the pressure is directly in my calculation of the zenith wet delay. So all the pressure differences I have from my ERA 5 model, and they are also in the zenith wet delay. So I think the model should include the pressure differences, or the differences due to the pressure differences.
Yeah, thanks. In general, to all the speakers, do we have any recommendations we want to give ESA? I was thinking, so now with this ATAT, we already have a lot of corrections. We want to include some recommendations for split spectrum, maybe also especially thinking of the future of L-band missions. Yes, do you see any particular recommendation for ESA that we should bring up this afternoon? Or we are somehow happy with the atmosphere and what's being done now?
Is ESA thinking about a product of the basically co-registered stacks of the SLCs, a product that all the SLCs are already aligned? So I mean, we have everything to do that, and with these ETAD corrections, we are almost there really. I wonder if
we should recommend going to this direction somehow, you're saying.
Yeah, I think, I mean, imagine if the entire SLCs are already aligned, so a user only takes a cube of the entire SLCs. And since I mentioned cube, I think that's the other thing, that the data are too big. So I don't know even what to recommend, but that's a big problem, how to access all this data.
I would recommend going to phases, and at least for many users, I think it would be good. Okay, so I think we can bring this session to an end. I would like to thank again all the speakers and the audience too, and the speakers especially those joining us from very far time zone. Then I would invite you to join again this afternoon the technical session on recommendations to ESA, and to visit also the poster session on these topics. So thank you very much, everybody, again, and bye-bye.
Thank you.